Hello everybody, this is Sky Darmas. Recently I've done this interview with Rupert Sheldrake, but it's already 2 months ago that interview happened, and a lot of new research has taken place since then. So I want to guide you through one of those new things that have emerged. So in that interview I talked about pretty much at the end of the interview, I talked about the Kepler's third law and how the distances in the solar system are really different from the mainstream because the equivalence principle is wrong. So if the equivalence principle is wrong, a lot of math looks a bit different. So when you do Kepler's law, let's look at the mass formalism. When you take m over there, it cancels. In the mass formula, it cancels out, but it's still the contribution to the g value is still there. So these are the Newtonian semi-major axes here in kilometer also. And then using this formula here and using the g values of the different planets that I calculated in the chapter about the perihelion precession of Mercury, we can calculate the SPD Kepler ratios of the planets and the SPD semi-major axes, which is basically the semi-major axis is the radius of a planet. Basically, but because it's elliptical, so then it's called the semi-major axis. So the discrepancies in the distances are like this. You see the smallest discrepancies for Jupiter and Saturn. And basically that has two reasons. One of the reasons is because they were probed very extensively. Saturn was probed for over 15 years. And I think it's still being probed. And by the Pioneer, I think the satellite is called Pioneer. Pioneer 1, Pioneer 2, not quite sure. So they, for those outer planets, they use the direct telemetry instead of deriving the radius of the orbit from the orbit period, which for the inner planets is known much more precisely than the orbit radius. So they just use that using Kepler's law, they obtain the orbit radius from that, but they don't do this for Jupiter and Saturn. And another reason this agrees so well with SPD, the semi-major axis of Jupiter and Saturn agrees so well, is because basically Jupiter and Saturn's g values are the same as the g value of the Sun, and so that brings us back into a situation which is similar to Newtonian gravity, whereas for the inner planets, the g values of the planets are very, very different from the g value of the Sun. So so this is not new, but then what I found is, what I did before is I used the old Kepler data for the inner planets and then used the modern data for the other planets. I was mixing two different data sets, and that's a bit messy and not really very meaningful because the Kepler data is very, very old. It's from the 17th century, and so what I did recently is I thought maybe, just maybe, the true, so this is still the unchanged, so I thought maybe the true hierarchies of the planets are still hidden there if we just separate the inner planets, the outer planets, and look at the hierarchies separately, When we do that, for example, for Allen 1963, we find pretty good agreement in the hierarchy here. Not perfect, but yeah, slight agreement here. And then here we see it goes down, up, down, and here we see it goes down. So basically, what I did is I just took just the inner planets and looked at the hierarchical order that is predicted. And using Excel, you can do that very quickly. And you see, okay, the hierarchical order is pretty good. But I wanted to see that in the diagram, and it was impossible to see because the graphs for the predicted ratios and the semi-observed, like not really observed, but sort of observed ratios were separate, and so you could not zoom in to really see the shape of the graph there. And so what I did is I multiplied the I scaled up basically the Kepler ratios of Allen 1963 so that they match up for Mercury. So then we can, it's like zooming in. And I also calculate the p-value of that, which is 3% that it's a coincidence, 3% chance that this is a coincidence. Then I did the same here for, this is Allen 1973. See, this goes down, up, down, and this goes down, up, down. So that's actually perfect agreement in the hierarchy. And here, yeah, not so good. So we get a total value of 5% chance that this is a coincidence. Then this is very bad data by Standish. What he did is, what they did, Standish and Williams, they just made everything centered around Mars, so that Mars has the perfect Kepler ratio, which is the perfect average of the whole solar system, and all the other planets were basically neglected. But you shouldn't fine-tune any planet to using Kepler's law. You should observe the actual distances using telemetry data. Here we have Arthur Cox 2000, which is he wrote the fourth edition. He made the fourth edition of Allen's astronomical entities, and because Allen had died already, passed away. So here we see the hierarchy is correct here, but here it doesn't fit at all. So, but for the NASA data is the best. Here we can see it goes down, up, down, down, up, down, and this is down, up, and it actually goes slightly down. If you were to zoom in on it, it goes slightly down. So it's a perfect agreement here. Well, I'm not sure if this is supposed to go up or down. Not quite sure. I would have to check my Excel file. Well, it doesn't matter. So this one is a perfect agreement. This this probably isn't perfect because this is supposed to go up, I think, and this goes down. So anyway, but pretty good. It's 2% chance that this is a coincidence. So if you add everything up, and you need to be very quite clever about how you're about to calculate these odds here. So when you have a case like this where the hierarchy is basically the opposite of what you predict, you calculate the p-value of the inverse hierarchy, and then you subtract that from 1, and that's your actual probability there, and it's more than 0.5. So this would be more than 0.5 because it's actually like negative evidence, and you have to honestly put that in there to calculate the true odds. Yeah. So we can rate the data here. Kepler is still, when you judge by the hierarchy, like not with how well the graph agrees, like Kepler's original data, where is it here? Like that's a huge discrepancy for Mercury and for Saturn. But in the hierarchy, it's pretty good. It's like almost perfect. Yeah, that's how you calculate the odds. I actually filmed a video about that, just about how you calculate the odds, the p-value of a hierarchy, but it wasn't very professional, the video, and I didn't post it. I will try to make another video about that, a more elaborate one. So yeah, you have factorials here. So if it's a perfect hierarchy, you have 1 over 6 factorial here, because you have 6 planets here. So anyway, until this day, Kepler data is still the best one in terms of the displayed hierarchy. Where is the list here? Because it's totally 100% unbiased, and for all the other data, to just evaluate the data, we have to split the inner and the outer planets because they're using a different methodology. The outer planets are measured more purely, more directly, and the inner planets, they're only sort of measured, but then the measurements are getting kind of ignored, and only the Kepler's law is mainly used to derive the semi-major axes, and the actual measurements take the back seat. They're just become like some small factor in the final value, like not the actual. It's not, those are not actual measurements. Basically, they're tainted by theory, you could say. But Kepler's original data was pure, and the data of the outer planets is relatively pure, and we can see that for NASA it's pretty good. We can see that it follows the patterns quite well, and also for the somewhat older here, Allen, 1963. Then over time it got more and more corrupt, but now the NASA data is kind of you can still see the patterns there. It's a kind of a compromise between following the theory and following the real data. Okay, that's all for now. Hope you enjoyed the video. See you soon.